So we're talking about transients and that kind of stuff. And I want to talk about Q switching today, which is a very popular and useful transient, which is used in lasers a lot. We'll talk about mode locking next, which is also not a transient, but it's a very interesting time domain thing. So today it's Q switching. This is just basically a way to create giant pulses. So it's called Q switching, but it's, well, it's very, I'll tell you why. So here, imagine you got a cavity. Here's your laser. You got some gain in there. And what you do is you add a shutter. And just like on a camera, except a very fast one, it's closed and then it opens. So you have this loss which you can remove from the cavity. That's why it's called Q switching. When the shutter is closed, you have a very low Q cavity. When the shutter is open, you have a high Q cavity. So what we're going to do is we're going to turn on the pump. So you got this thing just sitting here passively. You turn on the pump. And the shutter is closed. And so this is a very, very lossy cavity. Yeah, so what happens? Well, you turn on the pump. The inversion starts to grow. You've got your dn dt, dn2 dt equals your pump rate minus n2 over tau2. And there's no stimulated emission, obviously. So what will happen is in time, if you just turn this on a step, your population starts to grow. It'll eventually reach some steady state of R tau. And that's it. And it's just there and glows like a light bulb, and that's the end of it. Now, the goal here is to have a system where the threshold gain is maybe down here. And we're pumping this thing, and if the shutter were open and we turn on the pump, what would happen is the population would grow up to this point, then it would start to laze, and you start to get stimulated emission, and the intensity would just, start at some nice level, and the inversion would clamp right there. And you have this nice CW laser. Well, we've got the thing closed. We've got the shutter closed. And so the inversion just keeps growing and growing. And then at some point, usually about when we're 2 to 3 times above threshold, way up here, we open the shutter. And so now, suddenly you go to a high Q situation. And so now you got all this gain sitting here in this nice cavity. And so some of the spontaneous photons are going out. One lucky photon is going to, excite your mode. And it's going to go back and forth and see this ridiculous amount of gain every pass. So it's going to start building up. And it's going to very rapidly build up. So you open the shutter here, and this photon starts building up. And then a separate axis for intensity. And I'll show a plot of this. Suddenly, those start building up, and then it starts getting big, and it just, wham! You get this huge pulse. And when the pulse goes up, it's going to, of course, start saturating the gain. And the gain saturates. When it gets to threshold, that's when the pulse stops growing. But so long as there's more gain than threshold, the pulse keeps going up. So the pulse grows like crazy until this point here. Then it finally rolls over. This typically happens at an intensity way above what the normal saturating intensity would be. There's a lot more photons in this cavity than the population can sustain. So it continues the stimulated emission, but of course the gain is less than sustaining it. So the pulse dies, but it continues to saturate the gain, and the population goes down like that. So what it does is it basically sucks every atom out of the inversion, or every particle out of the inversion. So we pump, we integrate, we store some energy up in the system, then we open the shutter and extract it in one quick fast pulse. And now we're way below threshold, and then you start the process again, if you want. But the result is a very short, high energy pulse here with an awful lot of energy. So you can integrate this thing. And the good systems are things which have very long lifetimes. So if you've got like 100 microseconds of lifetime, you can pump this thing for 50 to 100 microseconds, build, store a lot of energy up, and then when the light goes, and I'll show you the fast, you can make the light come out. The pulse builds up very rapidly, speed of light. You can get a 10 nanosecond pulse out of this thing. So you get this kind of transformation of energy. I pump slowly for 100 microseconds, and I extract it all in 10 nanoseconds. So that's already 1,000-fold amplification of my energy rates. So it gives you nice giant pulses. And these are used for all sorts of things. They're used for ranging. When men landed on the moon, they started ranging with a ruby laser up to the moon. It was a Q switch pulse going up there. They're used for drilling, for soldering, welding. LiDAR uses these things. So anywhere you need a pulse and you'd like a lot of energy in it, the Q switch is a great way to go. So today we want to go through the math of how that comes about. So it's going to be ugly, it's math. If you read the book, we're in chapter 9, he before getting to Q switching, he goes through all sorts of transient stuff. And oh God, it's deadly. Have you read it? No, shame on you. You're supposed to read chapter 9. But anyway, it's really awful stuff. It's just very detailed stuff. We will go back to it, I think, if we get into, say, modulation of a semiconductor laser. Some of that stuff is interesting, but it's hyper detail and it's just a bunch of symbols and doesn't mean much. So I'm going to skip over that transient stuff. We'll come back to it when we need it. But I do want to talk about the transient of the Q switch. So I think once you start to see this, you're going to see the same kind of process. We're going to go through these equations, make some approximations, come down to a simple coupled set of equations, and they'll describe the transient. And when you look at the equation, you go, yeah, that makes sense. It's kind of self-evident when you see the equation. I could write the equations down and probably talk you through them and you'd buy it. But we'll drive them just to torture you. And then when we go and look at transients, you'll start to see the same phenomena again and again. And so I think this is a good foundation before we do the transient stuff. So let's try and develop an equation which describes this. So this will not be fun. I've got this cavity, and I'm going to deal with a couple things. I want to know what's the NP is the number of photons. So it's not the intensity, it's the number of photons I have in the cavity. So I'm going to try and compute that, because that's going to be the number of photons in this pulse. And if we look at, say, your standard cavity, we've got our two mirrors, whatever. You've got your two mirrors, and they've got their reflectivities, and I've got some gain medium here, and it's got e to the sigma NL for gain, but it's also got transmission losses on the windows, and I've got a shutter here, and it's also got transmission losses on the shutter and so forth. I got lots of things going on in this cavity. So I want to compute how much power is retained and how much is lost in a round trip. So we've done this about 1,000 times. So the rate at which photons are lost, dNP dt, is just going to be, take a blob of photons, run them through. 1 minus whatever's left is what was lost. So it's going to be 1 minus what's retained? R1, R2, T, so T to the 8th. I'm going to go through 8 windows. I'll assume they'll have the same transmission. I'll have some sort of gain here, e to the 2, sigma, n, l. And that should probably do it. So here's what I'm putting in. I guess I have the signs wrong. This is -1. Here's what I'm putting in. I lose that per round trip. Divide by the round trip time, 2d over c. And here's my number of photons. So I start with NP photons. I have that many after a round trip. The difference is how much I'm changing. This is my round trip lifetime. So this is the rate at which photons come or leave. If my gain is enough to make this term positive, then my photons start increasing. If my gain is not sufficient, then I see that I'm losing photons every second. So I'm starting to lose them. So depending on what the sign of this thing is, I guess that's right. I either have my photon number increasing or decreasing. And it just depends on my retention and the gain there. So we're going to kind of play with this a bit. Now, we have this issue with logarithms and exponential gain and stuff. And so The next couple steps are how can we get away from the exponential and get into a linear regime. So we're going to make some approximations here. So something you'll always see, people like to parameterize the loss into kind of a distributed. These are discrete. I have a loss at a point and a point and a point. And we'd like to replace that with something of the form e to the minus alpha t times the distance of the cavity. So here's d. So I make a round trip. I have a bunch of loss. I can describe that loss as an exponent. So this is equivalent to this thing here. R1, R2, t to the 8th. It's basically our losses. And so we like to distribute the loss in this exponential form. Then we can kind of compare our exponential gain to our distributed loss. And then we're going to relate our loss to threshold and gain to inversion and all this kind of stuff. So here's the step. But you'll often see this kind of step where we distribute the loss per unit length. And we say, okay, well, we can do that if we define alpha in this form. And we do it in kind of a handy way. We do 1 over 2d times the log. And notice I'm going to do 1 over R1 t to the 8th. I'm going to take R2 out because R2 is my output. And plus the log of plus 1 over 2d times the log of 1 over R2. Now why do I do that? This is internal loss, I guess I call this, and not very fun. We don't like this loss, but it's internal. It's light's getting lost inside the cavity and not useful. This is the external loss. This is actually the loss I like. This is the loss you put in so you can extract the power. This is useful loss, useless loss. But I can kind of separate these things in two ways. Now, so I've got my expression here, my gain and loss. When I look, yes?
So why for the external loss you multiplying again?
Whoops. This is a mistake. Yeah. It should be important. I got it there. I didn't, yeah. So here's where we start doing kind of the approximations. My gain and my loss, if I look at this term here, I've got an e to the minus 2, let's say alpha minus gamma d, and gamma is just your sigma NL. So here's my gain, gamma for gain, G for gain. Here's my alpha for loss. And so I'm just kind of looking at this term here. My photon, the rate at which my photons are changing is this kind of difference of gain and loss. And it's happening in an exponential form. And exponents are hard to deal with when we're doing math, so we'd like to get rid of it. So we're going to say, you know what? Let's assume this is not that big. We're going to make the approximation that, you know, e to the 2 to the alpha minus, I'll do it this way, gamma minus alpha is approximately equal to 1 plus 2 gamma minus alpha d. So I'm going to make a first order approximation of my exponent. How good is that? If alpha plus, if this exponent term is on the order of 0.2, you know, 20%, 20 to 30%, this is a pretty good approximation. So if we find on a round trip our light is not increasing beyond about 30% per round trip, this is fine. If it's tripling, you know, I mean, if it's going up 100% or something like that, this is not such a good approximation. But this is not atypical of most of our lasers. So typical lasers like this, you're going to get, you know, if we pump it maybe 3 or 4 times above threshold, we might have a gain of 20, 30% per pass. And so this is not a bad approximation. But if you get in a situation where you got a gain of 10, this approximation is crap. You know, you'd have to go back and do more rigorous analysis. But the reason we're doing this is we want to get to kind of a linear domain. So we're going to make this approximation and replace our exponent with that approximation. Then you plug it into here, and you're going to see your differential equation in photon number becomes much simpler because we get rid of this exponent. And so you plug it into that, and what you're left with is, so this is just a simplification step. You get the rate of change of the number of photons in the cavity with respect to time is just going to be 2 times gamma minus alpha total times the length of the cavity times the number of photons divided by the round trip time. And the round trip time is just 2d over c or whatever it's going to be. So I've taken this, which has this term here, and I made it something simpler to look at. And so long as this is not a big number, this is a very fine approximation. But I stress it's an approximation. Your gain has to be something on the order of 30% or less. But I've got an equation now for the photons dynamically. Now, we have round trip times, and we have cavity lengths, and we've got losses and all sorts of stuff. And so the book kind of goes through this, but you can put a lot of this together in a term we all know and love, and that's the cavity lifetime, the photon lifetime. So you've got a cavity, you've got round trip travel time, you've got losses and decays. We characterized how long does a photon stay in there, and we got the photon lifetime. And remember, the photon lifetime was equal to the round trip time divided by a whole bunch of stuff, 2 alpha total times d, where alpha was this distributed loss. So you can see a lot of those terms in there, and you can say, okay, you know, we can add and subtract and put these things all together. And we like to deal with Q-switching in terms of the photon lifetime. So we're going to kind of do it in that unit. And so you put that together, and you get, you know, this equation keeps moving. So the number of photons per second, dn p dt. I can't even read that. I still can't read that. Becomes 2 alpha d over tau round trip, gamma over alpha minus 1 np. I do some magic here. And then, what did I just do there? I think I jumped ahead here. Oh, okay, this should be tau photon. There's my. Okay, so if we make that substitution here and we get this expression. Oh, this is completely wrong. God, I'm sorry. This, you plug that into that, and you get 1 over tau photon. That's what I wanted. Times gamma over alpha minus 1 times number of photons. And so here's where I'm trying to get to. So this is all just, that's that formula equation over there in new terms. Same thing, just small signal. Okay, so that's kind of where we want to go. Now, the last step. This is my gain. Gain, remember, was sigma NL. My loss was the loss per unit length. And what's the loss? Well, the loss, I can relate that to my threshold inversion. My threshold inversion, if I have a loss alpha, that must be the same as sigma N threshold loss. So that's a very important step here. One reason we're kind of doing this alpha stuff is that I want to get my losses in terms of my threshold. My gain is, of course, in terms of the inversion. And so I'm going to go one step beyond this. If I multiply both of these by, you know, well, if I replace them by their form here, I notice a lot of terms cancel out. I'm going to be left with populations. And so this becomes 1 over tau photon times the initial inversion, let's call it n naught, divided by the threshold inversion minus 1. And let's look at that. So the rate at which photons increase, I've got my lifetime, my photon lifetime, but it's the ratio. If I have more gain than the threshold gain, photons increase. If I have less, of course, they decrease. So, and the rate at which they increase is just proportional to the inversion. So if I have twice threshold inversion, I get twice as much amplification as and 3 times and more. So it's a very nice way to relate my inversions, which is what I'm really worried about, to my photon number. So because at the end of the day, I want to say how many photons am I going to get out of this. So I have to relate that to my inversion. So I'm going to do one more step. This is the number of photons in the cavity. It's not the intensity in the cavity, it's the number of photons. And the photons are going through this gain medium, and they're interacting not with n, which is number per cubic centimeter. And it's just a raw density. They're only dealing with, there's a finite number of atoms in here. So we've got this volume, and I've got these number of atoms in here, and the best I could do is talk to every one. So I'm actually talking to a certain number, and not a density, but a number. So if I multiply both these by the volume of my mode, what I'm going to be left with, if we look inside this gain medium here, here's your gain medium, and we've actually pumped this little zone right there. And it's the number of atoms inside that zone. That's the total number of atoms I can interact with. And that the best I could do is get a stimulated emission from each of those, and that would be my number of photons. So I don't worry about the density. I need that for gain, that kind of stuff. But what I really want to know is, what's the total number of atoms? You know, just how many atoms, total number. Not density, total number. You know, if I've got 150 atoms in there, the best I can do is extract 150 photons. I don't care how dense they are. You know, it doesn't matter on density, it just means how many photons, how many atoms can I extract from. So when I multiply by volume times the density per cubic centimeter, I'm going to get the number of atoms that I'm interacting with totally. And so the final form of this expression is 1 over the photon lifetime, and I'm going to little n over little n threshold minus 1 times the number of photons. And this is really the working relation we want, because it relates the number of photons we're going to generate to the total number of atoms we can invert. And if I have a bigger volume, that'll be a bigger number. I can potentially get more power out of this thing or more energy. So the key thing is the total energy you're going to get out of a pulse depends on the total inversion you started with. Yeah.
Volume matter, because you're multiplying by volume on top of volume.
Well, it doesn't change anything in terms of the rate, but what it does, it relates it to the number of atoms in the cavity that I'm dealing with. So here it's just an inversion, you know, and so.
Because this is the ratio still the same.
The ratio is exactly the same. I mean, that's exactly right. The equation hasn't changed. But I guess what I'm going to say, we've been concentrating always on the number density of the inversion for gain. For Q switching, I really don't care what the number density is. I just want to know how many total atoms can this thing interact with. What's the total number of inverted atoms? Because again, as I said, you know, if you know, my number density might be huge, but if my volume is small, and I'm only going to interact with 100 atoms totally, I will never get more than 100 photons out of the system. And what I want to know is how many photons am I going to get in my pulse? And so what I'm kind of doing is scaling in the size of the beam and everything into this. So my beam size matters now. So, okay, so this is one of our equations. And it relates photons to my inversion. And again, as I said earlier, I think if you look at it, it makes sense. You know, if that's bigger than threshold, of course the photon density increases, and otherwise it doesn't. Okay, now let's see if we can get a rate equation for the population. How is the population affected? So when we have photons increasing, that's great, but we have stimulated emission, so the inversion must be reducing. So there's got to be a similar rate equation for that. Oh, God. No, I'll do it over here. That one's pretty easy. We've got these levels here, and let's say it's a 4-level system. We're pumping, relaxes. Here's our lasing. So here's N2, here's N1, and our little n is just N2 minus N1 times the volume. It's the inversion. What's the total inversion we have there? Now, what happens to the inversion when I have stimulated emission? So I've got an inversion of n, maybe it's, I'll use a simple number, let's say 100, okay? I bring a photon in, 2 photons leave. So I have stimulated emission. What's n now? So I stimulated emissions, I took one from here, I put it there. So this is reduced by 1, that's increased by 1. So delta n equals 2 for a stimulated emission. Now, we make the approximation that the bottom relaxes really fast. And that's usually still true. But for the Q-switch analysis, we're going to assume that this pulse happens so fast that there's no relaxation. So we're going to massively kind of overestimate how sluggish this system is. The pulse will probably actually work better than we guess. But we're going to make an assumption that whenever stimulated emission occurs, whenever there's a dNP by 1, the inversion suffers a loss of 2. Because we take 1 from there, we add 1 there. And so you can just simply write that down. dN dt equals minus 2 times n over n threshold times np. Because this is the rate at which they're being generated. And I need to do some more math here. So I'm going to, I can do a change of variable. I'm going to let capital T equal T over tau photon. And so I really should write this as dN d normalized time. So I'm going to do time in units of photon lifetimes. And then this equation looks like this, minus 2n, which is what I wrote. So what I wrote was not quite right. So in terms of photon lifetimes, the population changes at 2, twice the rate of stimulated emission. And in terms of this new normalized term here, the photon decay, or the change in photons, dN photon, d capital T, the per unit photon lifetime, just becomes n over n threshold minus 1. All right, a lot of golf math. I didn't do a good job on that, but anyway, these are the equations you get at if you do it carefully and thoughtfully, which describe the time rate of change of the photons in the cavity per photon lifetime, and the time rate of change of the inversion per photon lifetime. They look very similar. So what we have now is 2 coupled equations, and they describe how these operate. So clearly, as the photons start to build up, the inversion will reduce. That's going to affect how fast these build up, so they're coupled very strongly. You can't plug one into the other. They're not linear, they're nonlinear. So this is as far as we can go in terms of solving these things. So if you want to really solve these things, you have to numerically do it. So I'll show you a plot of that in a minute. But we can do a couple things in the meantime and kind of gain some insight into the Q-switch process. Let's stop here though. Do these equations make sense just conceptually? Is it just symbols on the board, or does it make sense to you? Should we start over? So I hope it makes sense. I mean, this is the uninverted. I mean, so this is your inversion over threshold. So this should be a positive number. So if this is a positive number, we have gain. And then when we have stimulated emission, it should be reducing. And if I stimulate that many, well, I'll knock the thing down by twice that many. So I hope it makes sense to you. But they do couple the inversion to the number of photons. And I'll solve them numerically in a minute. I can take the ratio of the two. If I take the ratio, you get an equation like this. dNP dN equals 1/2 n threshold over n minus 1. Okay, great. What the heck does this mean? So I can rewrite this in terms of photons. So I've got dN photon equals 1/2 n threshold over n minus 1 dN. I can integrate both sides. And now I can see how the photons relate to a change in population. And so I'm going to integrate this. And I'm going to integrate from, I've got this pulse. Here's our time domain. We get this pulse, and it's going up like this and goes back down. So here's the number of photons as a function of time. Now let's go from 0 to max. Let's just define it. Here's n max. And I kind of like to figure out how many photons are in this pulse. And what do I know about the inversion at these moments? So I'm going to integrate this thing. And I'm going to integrate from 0 to n max. Do I know anything about, what are my limits then on the inversion? Well, when I'm at 0 photons, my inversion, here's my inversion, as a function of n is maximum. It's equal to my whatever the n naught is. So it's at the initial value. What is it when I hit the peak? So when I hit the peak of my pulse, you saturated the gain down to where? We know that when we hit the peak of the pulse, the gain equals the loss, so the gain must have saturated down to the threshold gain. So here's this value here at the peak of the pulse is n threshold. So I can integrate this, and the limits are consistent. Before the pulse starts, I have no photons, and my inversion is maximum. When I'm at the peak of the pulse, my inversion is saturated down to threshold. So I can solve that. And I guess I'm going to do a one-board lecture today. And so you get the max, n max, what's the peak number of pulse photons we have in this thing, is given by n initial minus n threshold over 2 minus n threshold over 2 times the log of ni over n threshold. Okay, n max, that's the top of the pulse. This is going to be my peak power. So I can relate, if I know I've got n max photons in the cavity. So what's my power? Well, I know my power is they're leaking out at a certain rate. I know my lifetime. I know how fast they're leaking out. And so I can compute and I know each one has photon energy h nu. So I can get a rough idea what the peak power is in my pulse, an equation like that. And you see it goes up, the larger my initial inversion with respect to threshold, the more my peak power is. And then there's just this kind of cleanup term here. Okay, it's not great, but it gives us a sense of what's going on. I want to note that this is the cavity lifetime represents power going everywhere. So the amount of power which actually comes out is a fraction of that. But basically your power coming out, your peak power, is going to be n max. It comes out over I've got that many photons in there. Every round trip, I'm going to lose 1 minus R2 of them. And so that gives you a rough idea what that is. So it's kind of cool to see what your peak power is, get out of that. So, times h nu. So we can get something out of this directly. It's kind of useful. It's more interesting to see, well, how much of our, yeah, question?
You take the ratio of DNP and DN. Where does, DN, big T has an NP in it? Do you
No, where'd that go? Oh, you got me here. I don't know. Oh, here's where it went. Okay, yeah, I left it off there. That's good catch. So, all right, so we play with these math equations. We can fool around with that. A more interesting question is, how much of the inversion is left after the pulse? So I'm going to do the same trick. I'm going to look at this equation, and I'm going to integrate from here to here, which seems kind of weird. So I can integrate from 0 to 0, and so that's going to give me 0 on this side. And I'm going to integrate from n naught to n final here. And so what you get when you do that is it's going to be a similar looking equation here, but it's going to be 0 equals n initial minus n final over 2 minus n what do I get here? I get minus n. Yeah, minus n threshold times the log of, this didn't look right. I think it's n initial over n final equals 0. Okay, so you get the same basic equation like that, except now it's got different term limits. This also is a transcendental, can't be solved. And so when you do that, we'll change boards here. You can solve that for n final over n initial, and you get this mess, e to the minus ni minus nf over n threshold, which is again a transcendental equation. So it has to be solved numerically. But it's been done 1,000 times. And what you find, if you make a plot of, here's ni over n threshold, say 1, 2, 3, 4, and here's ni minus n final over ni. So if n final is 0, this would be 1. So I've used the 100% of the inversion. You could get a curve kind of like this. And if you're at 3, if you go to 3 threshold, you pull 94% of the inversion out, which is pretty good. So, 94%. If you go to 4, you get 97%. So the marginal gain becomes less and less here. So if you can pump your cavity up. Remember how we did this pumping? Here was our inversion as a function of time. And if we pump it long enough so we are 3 times above threshold, when you fire your Q switch, you're going to extract 94% of the stored energy in that pulse. And I don't have other numbers, but it's not too bad. Even at 1, well, at threshold, you don't get it. But at twice that, you get like 80%. So it's pretty effective at pulling the energy out of these things. So what I want to do is show you now to a numerical plot of what it looks like. So let's say you take these equations now and just plug them into a computer and grind it through and solve them and watch the dynamics of how this works. So let's see if we can get this working. I've never used this lab or this computer in here. So this will be a bit of an adventure. Touch screen to begin. Okay. Computer, laptop. Okay. Oh. All right. So I got a Mathematica code here which I wrote, which simulates a Q switch pulse. Oh, for heaven's sakes. Okay. Cross your fingers. Yes. Okay. I want, I'll just punch a button and see what changes. That looks a little better. Okay. So I've got a Q switch here. Okay. So here's a little code I wrote. It's pretty simple stuff. But notice at the top I defined the volume. This is work I did for Lockheed Martin. They wanted to know some ways to make some quick 800 nanometer pulse lasers. So here's our volume. So this is just the area of the mode times the length of the cavity. I chose mirrors of 93% and 99% to make this thing operate. P, that's my pump. I'm going to pump with 2 watts. And then my pump rate, R, is the pump power divided by the photon energy divided by the volume. So that's how much energy I'm putting in per second into this thing. Tau is the lifetime of my excited state system. This is Thai Sapphire, so 67 second. No, this was chromium. This is a chromium laser. Okay, doesn't matter. Round trip time of the cavity, 1 nanosecond. It's a fairly short cavity. I'll show you what happens when we change that on the pulse. Then the gain cross sections right there, sigma, round trip lifetime, the cavity lifetime. That's my photon lifetime. It's just the round trip divided by those losses. Threshold, I compute the threshold gain right there. Then I start changing things. I'm going to do steps, 1 nanosecond steps. I'm going to have an inversion of 3 times 10 to the 18th. And I'm going to start with 1 photon in the cavity. So I assume my pump has been running for a while, and I let it rip. So then I've got this crazy do loop, and my programming is awful, so do not look at this as if this means anything. But it computes what I just did. I just took that DN and I just step it through one at a time. You know, here's my DN. I adjust add my DN to my Inversion, my dphi, add the dphi to that, and then just keep recycling and run it through.
What does the table function do?
Which function?
Table function?
Table, I'm just creating, this is, where was that, here?
Yeah.
I'm just creating a big list of my data. That's all I'm doing. I'm not a programmer. This is mathematics. This is how I did it. I'm sure there's better ways to do it. But I'm just creating a big list of data. Here's the data that comes out. So I put those numbers in and say, okay, fire. And I started with 1 photon in the cavity and let it rip. So it starts riddling around. These are round trips. But these are nanoseconds. Yeah. So it builds up. And eventually you can see the power starts to build up and you get a pulse. And that blue thing is a pulse. And the yellow is the inversion. And you can see the inversion is just pretty indifferent on this time scale. We made this assumption that what is that? That's outside, right? Okay. We made the assumption that things are changing slowly with respect to the pulse. So we're pumping, we're putting atoms in all the time, but over this time scale, the inversion hasn't changed at all. But as soon as the pulse starts to build up, notice the inversion starts to drop. And it starts really coming down. And then when it reaches the peak, it hits threshold. And I've computed threshold, that number there, 1.03 times 10 to the 18th, based on my mirrors and gain, all kind of junk. That's my threshold inversion. And remember, I put it at 3.5. So I started about 3.5 times threshold now. So when it gets down to threshold, which is about here, notice where the peak of the pulse has occurred. And then it keeps, so now I got a lot of intensity here. And so it keeps on saturating the gain. These photons are still going back and forth. Every time a photon goes through, it saturates. It doesn't know that it's above or below threshold. If the gain is below threshold, there's less gain each round trip, so you see it starts falling, but it keeps stimulating. At the end of the day, that's what's left. And so I think I computed, I forget, I got 67 microjoules out of this pulse here. But it shows you kind of dynamically how you do this. So I put these two equations in step by step. Let's change some things. What if I were to reduce the gain? I'll take it down to 2.5, not W.5, and see what happens here. So I need to take more steps here, but notice what happened. It took a lot longer for this pulse to build up. It's not saturating as deeply. It's a longer pulse, kind of fatter. If you wanted, this looks like a 30 nanosecond pulse or something. If you wanted a 5 nanosecond pulse, this is not so cool. So by firing the shutter before the gain got up there, I get a softer pulse. I'm not extracting as much energy. What else can we do? So having a lot of gain is nice. So I'll put the gain back up there. What if I have a shorter cavity? Here's my round trip, 1 nanosecond. Well, let's just try. Let's make it 2 nanoseconds. I think I'm gonna have to do. Let's just see what happens. It may not. Yeah. Okay. I'll have to do more runs here. Okay. So if I make a longer cavity, what happens? Well, it just takes longer per round trip. So everything slows down a bit, but I do get a bigger pulse, a longer pulse in time, and that's because it takes long. Every round trip I'm saturating the gain, but the pulse is now twice as long as it was. If you want to make a short pulse, you want to get that photon lifetime really short because it just makes a lot of round trips quickly and bleeds out. So if I make a shorter, a smaller round trip cavity, instead of where's my round trip? I've lost it now. There it is, yeah. Instead of a nanosecond, let's make it half a nanosecond, which is a pretty short cavity now. You're talking something that big. But if you really want to make the short pulses, do it. Notice what happens. Everything happens on a faster time scale, and the pulse is dramatically shorter. So your pulse is proportional to your photon lifetime, that kind of stuff. So you can play with this all day long, and then you can again see the inversion, and you see the pump is starting to kick in. So we're starting to build the thing up again. So if we wait long enough, it'll get back up there, and then I fire it. So that's how you look at these things in the time domain, and you can do a lot of modeling and play with them and learn about it. Does that make sense? Anything you want to explore with that? Okay. Well, let me just finish up. How do you make a shutter? You know, how do we make these things operate as a shutter? So let's see if I can get this thing off. Yes, I'm sure. Cool. Okay. So the shutter is an interesting process. We've got a couple ways to do it. One is, I mean, people have tried mechanical, they've tried spinning mirrors, they've tried everything. The classic ways are electro-optic or acousto-optic. So you can make a Pockle cell. You just take a crystal, 2 electrodes on it, hit it with a high voltage, usually it's 1,000 volts or something like that, in a square wave, and it's a Pockle cell, so it flips rotates polarization 90 degrees. So you have this in conjunction with a polarizer, and this makes a very nice shutter. And within nanoseconds you can flip it, and so you just instantly change the gain from all loss to all gain, and get it going. Expensive, big, bulky, big power supplies. It's not for the lighthearted. But that's electro-optic. A cheaper way is acousto-optic. You take a crystal and you mount a PZT on it and you drive that resonantly, and typically like 50 megahertz or something like that, and that creates an acoustic wave which travels through the crystal. An acoustic wave is compression, rarefication, so the intensity, the index changes. And so light coming along sees this modulated index, and it looks like grating, and it scatters light into various orders, which is lossy. So you can kick in 10-20% loss with an AO cell. When you want a Q switch, you turn the signal off, and it goes away. Trouble is it takes time for this to travel acoustically. So it's going to take about 100 nanoseconds or more for that to clear out. So it's kind of a soft shutter. It turns on slowly. And so you tend to get a kind of a softer pulse out of these things. So it's not for the real fast. But the fun one is the saturable absorber. And that needs no parts at all. And all it is, you put some crystal in here, sometimes a liquid, but it's a material which has 2 levels which are resonant with your laser line. So it's got a transition. It's got an N naught and an N1, and this absorption is exactly in line with your laser. So, an example, you need an MEAG. If you put chromium 4+ in the crystal, chromium 4+ is a transition from ground state up to an excited state, which is at 106, so it absorbs light. And what you want to do is find something which has a large cross section and a long tau. So what happens? I've got my gain medium here, and I've got my cavity, and this is probably adding, so let's say 30% loss. So you start building up your gain and building up your gain, and eventually you've got so much gain in this thing that you've got 31% gain in this thing, so 30% loss. So light finally starts to flicker and starts to laze here. Well, these first photons are absorbed heavily, and so the first few photons get absorbed and they kick atoms from here to there. It's a long-lived state, so it doesn't take too long before you have equalized populations, and then it's perfectly transparent. So you sacrifice kind of the leading edge of this pulse to saturate the gain, but you saturate the loss by equalizing the populations, by absorbing some photons. Now it's perfectly transparent, and the Q switch takes off and does a great thing. And this can be very fast. So these are fast and really nice. And what's cool about them is there's no moving parts. You just put it in and it just works. The sad thing is here, I can exactly send a pulse when I want it. You want a pulse at this moment, bang, I can shoot it out. Here, you put it in, you turn on your laser, and it runs, it's just bang, 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 bang. And it's pretty repetitive, but you cannot predict, you can't control when the pulse comes. So if you just want to train a pulses because you're drilling a hole, you don't care, this is perfect. If you want to do very precise ranging and you want to start when you want t equals 0, you want to send a pulse, you're going to do something like that. But that's the basic idea. So things which can fairly quickly open up. It's got to be sub-microsecond. Ideally 10 to 20 nanoseconds be the way you do it. All right, that's technology. So okay. Time's up. Perfect time.